Hello, what's on the menu for today? The sum of the periodic monotonic divergent series of 1, 1 plus 1 plus 1 plus 1, etc. to infinity equal negative 1/2. So we're gonna go through 8 proofs. Proof number 1, generating function. As usual, we always start with the generating function, give us the answer straight away if the series is stable. Proof number 2, direct calculation. Proof number 3, intercept function. Proof number 4, partial sum integral, the PSI. Proof number 5, Ramanujan summation. Proof number 6, Abel-Plana summation. Proof number 7, Riemann zeta function. And proof number 8, Dirichlet eta function. All right. Proof number 1, generating function. So as usual, let gf of x be the generating function for the periodic monotonic divergent series 1. I'm using the square bracket notation to represent the periodicity 1 plus 1 plus 1. So gf of x is equal to 1 over 1 minus x, famous geometric series which expands as 1 plus x squared plus x cubed plus x to the fourth, etc. So if we write down that equation again in its expanded form and then we replace x with 1, we get 1 plus 1 plus 1 plus 1 plus 1, which translates on the right hand side 1 over 1 minus 1, which is 1 over 0, which is of course infinity. So infinity unsigned, and applying the fundamental theorem of a divergent series of integers, we conclude that the periodic monotonic divergent series 1 is unstable because its value at the value of x generating the function is equal to infinity. It's not a finite value, so it's unstable, and therefore we cannot determine the sum of this divergent series by evaluating its ordinary generating function with the value generating the series, x equal 1 in that case. So unfortunately, this one is not a proof. Proof number 2, direct calculation. So let's write down the divergent series or monotonic divergent series of natural numbers starting from 1, 1 plus 2 plus 3 plus 4 plus 5, etc. Let's open the toolbox. We have done a video on that one. We know that the sum of the natural numbers starting from 1 is equal to negative 1 over 12. So we can plug that in. And then let's write now the same thing, but single shifted to the right. So 1 leading 0. So 0 plus 1 plus 2 plus 3 plus 4 plus 5, etc. Which is also the sum of the natural number starting from 0. So let's open a toolbox. What is that value? It's a positive 5 over 12. So let's plug that value. Don't be surprised that those two values are different. Remember, the divergent series or monotonic divergent series of natural numbers is unstable, so you can expect its sum to vary when you add leading zeros or when you space with zeros, equitable space, determine of a series with zeros, the value will change as well. So when we have those two, what do? We do the difference, term by term. When we do the difference between two divergent series, we work term by term. What will be the difference? Let's check. 1 minus 0, it's indeed equal to 1. 2 minus 1, it's equal to 1. 3 minus 2, equal to 1. 4 minus 3, equal to 1, etc. So we do the difference of those two divergent series term by term. Therefore, we're going to do the difference also of the sum of those two divergent series. And then we get minus 1 minus 5 over 12. So minus 1 over 12 minus 5 over 12 means minus 6 over 12, which is, of course, minus 1 over minus 1/2. In sigma notation, we can write it like this. So the sum from n equal 1 to infinity of 1, constant 1, is equal of the sum of n equal 1 to infinity of n minus the sum of n equals 0 to infinity of n. The first one we've seen on the toolbox, negative 1 over 12. The second one is 5 over 12, so we plug those two. Let's not forget the minus sign in between here. And then we do the difference. You can see minus 6 over 12, it is definitely negative 1 over 1/2. Happiness. Proof number 3, intercept function. So let's follow the same steps that we follow as usual in all the other videos. Calculate the partial sums. That's the first step. So the partial sum of that monotonic divergent series is quite easy. Obviously, it's the counting function. We keep on adding 1. So 1 plus 1 equals 2, plus 1 equals 3, plus 1 equals 4, and so on and so forth. So really the counting function that we learn at primary school or nursery school. Then we express the partial sum S of n, uppercase n, that's my index or index notation for the partial sum here at the bottom, as a closed form expression. So the sum S of n is the sum from lowercase n equal 1 to uppercase n of 1. I open the toolbox, but it's a little bit trivial there. Obviously, the sum over n times the constant 1 is equal to uppercase n, the number of times that we sum n. So we plug that in. So the partial sum from lowercase n equal 1 to n is equal to n. Calculate the intercept point h of n as the half sum of two consecutive partial sums. So by definition, h of n is s at n minus 1, so the partial sum at n minus 1, uppercase n minus 1, plus the partial sum at n divided by 2, because we take the arithmetic average. So the first one is, of course, n minus 1 over 2. The other one is n over 2. So if you combine those two, you have 2n over 2, which is n minus 1/2. All right. So there, because we don't have the value here at for n equal 1, so we assume s at 0 equals 0. In other words, we assume that what is on the left here hasn't started yet, so we set it at 0. Express a continuous intercept function h of x by replacing uppercase n with x. So what we mean by that, we're just replacing the discrete variable by the continuous variable. Wherever you have n, you plug x, x being a real variable. So the function is a straight line x minus 1/2. Okay, and let's get more space on the next board. There's more space, we can finish the proof. So step number 4, we evaluate h of x, where x equals 0. So obviously x minus 1/2 for x equals 0 becomes 1/2. After projection on Q, let's not forget to project. We obtain the sum of the periodic monotonic divergent series 1. So the sum from n equal 1 to infinity of 1, which is again in its expanded form 1 plus 1 plus 1 plus 1, etc., is equal to that intercept function at 0, which in other words the intersection of the intercept function with the vertical axis. We project on Q. It's already a rational number, so projecting on Q doesn't make a difference in that case. We plug that in and it's equal to negative 1/2. All right. So if we look on a graph, how does it look? Here it's the different steps. It's a staircase from n lowercase n equal 1, the partial sum is equal to 1. Then for lowercase n equal 2, then we have 1 plus 1, so the partial sum is equal to 2. And then for n equals 3, the partial sum is equal to 3, obviously 1 plus 1 plus 1. So it's a staircase. That is the intercept point. Those are the intercept points. So again, it's not halfway through the blue line. It's not here or there or there. It is halfway through the gap between the previous one that you can visualize here being flat here because it's 0. So halfway through the gap, it's here. Then we go here. Halfway through the gap is there. Halfway through the gap there, and so on and so forth. So you can see those ones give us, they are aligned, give us a nice line that going through there. The function here is h of x equal x minus 1/2. We just seen it on the previous board. And then that value is here. It's the intersection, like I said, of the intercept function, which is a straight line here, with the vertical axis. So you can see the intersection is here at negative 1/2. So that is visually where you find the sum of the divergent series or periodic monotonic divergent series of the constant 1, 1 plus 1 plus 1 plus 1. All right. Partial sum integral, the PSI. So now let's use the PSI method to find out the same result that we already figured out from the previous proofs. Step number 1, calculate the partial sum. We have seen it already, let's not repeat, it's quite trivial. So it's the counting function, so the partial sums will be 1, 2, 3, 4, 5, etc. Step number 2a, express the partial sum S of n as a closed form expression. Again, easy. The partial sum, we have seen it on the previous board. It's quite easy and trivial. It's the number of times that we have the constant one, so uppercase n. Here it is. N being an integers or a natural number. Step 2b, express the continuous partial sum s of x. So we write the same thing and we replace the discrete variable n with the continuous variable x as a convention, of course. Calculate the PSI. So by definition, the PSI is the integral from -1 to 0 of the continuous partial sum s of x, and we integrate that one. So it's, of course, because s of x is equal to x, so it's the integral from -1 to 0 of x dx. So again, you know the formula. When we integrate x to the power n, it's x to the n plus 1 over n plus 1 plus a constant of integration. Because we have defined bounds for that integral, we can ignore the constant of integration. It will cancel each other out. So we can simply write that it's x squared over 2 integrated from -1 and 0. So that gives us, of course, 0 squared over 2 minus -1 squared, which, of course, it becomes equal to 1 over 2. That one is gone, and we're left with -1/2. Exactly what we expected. So finally, the sum of the monotonic divergent series of constant 1 plus 1 plus 1 plus 1, etc., is equal to the PSI after projection on Q. We expect a rational number here. We plug that in, and that's what we have. So, of course, it's already a rational, so projecting doesn't make a difference. We already have the result. Cool. If we plot that on a graph, you can see the line here with a function s of x equal x. So it's obviously the 45-degree line here going through the origin, and the integral from -1 to 0 of that function s of x. You can see it's from that bound to this one. I put it in red, highlighted in red there, because it's below the horizontal axis, so it's a negative. You can see it's a triangle which is half the unit square here. So of course the surface is 1/2, obviously, because it's below the horizontal axis. It's -1/2, not +1/2. So that's where you visualize also the value of this monotonic divergent series or periodic monotonic divergent series of constant 1. It's the surface here of highlighted in red. Proof number 5, Ramanujan summation. Let us apply Ramanujan summation method. So sum from n equal 1 to infinity of f of n, as per Ramanujan's formula. It's a negative f of 0 divided by 2, minus the sum from m, I changed the index there not to confuse, m equal 1 to infinity of the even Bernoulli number, b to m divided by 2m factorial, times the 2m minus 1, so odd number, 2m minus 1 derivative of f evaluated at 0. So where, like I said, b sub 2m is a 2mth, actually 2m plus 1, because the Bernoulli number, we start to number them at b0, so strictly speaking it's 2m plus 1 Bernoulli number. In a context, always when you use Bernoulli numbers, always keep in mind in which context you are, is that b1 equal +1/2 or -1/2. It's important. So in that case we are on a context of b1 equal +1/2. So let's use f of n equal 1, it's a constant, so it's easy. F of n equal 1. Of course, f of 0, because it's a constant, will be equal to 1. Let the derivative of a constant is equal to 0. Therefore, the value of the derivative at 0 is still equal to 0. It's uniformly 0. And that will remain true no matter how many times we derive after that. So f, the 2m minus 1 derivative of f at n is equal to 0. And therefore, the same evaluated at 0 is equal to 0. And that is true for any value of m greater or equal to 1. So because of that, any value m or equal or greater to 1, it's equal to 0, we can ignore completely that second term of the equation, and we are left only with the first term. And we know that value is equal to 1. So that gives us the answer straight away. The sum from n equal 1 to infinity of f of n is equal of the sum of n equal 1 to infinity of 1, that's the function that we have chosen, is equal to negative f0 over 2, or -1/2 of f0, which is, of course, -1/2, what we were expecting. All right. Proof number 6, Abel-Plana summation. So let us apply Abel-Plana summation method for the monotonic divergent series. So the formula is as follows: sum of n equal 1 of fn equal negative 1/2 of f evaluated at 0, like Ramanujan summation, start the same. But then it's plus I, the integral from 0 to plus infinity of f evaluated at it, minus f evaluated at negative it, over 2 to the 2 pi t minus 1 dt, t being our variable of integration. So if we use f of s, and now s is a naming convention for the complex variable, so f of s is equal to 1, still a constant. F of 0 is equal to 1, by definition of a constant. F of it is equal to 1. F of negative it is equal to 1, it's a constant, so it won't change. And then, of course, we notice that f of negative it is equal to f of it. In other words, f is even. If f is even, you can see here what's going to happen. We're going to end up with a 0 and integrating 0. So we obtain sum from n equal 1 to infinity of 1 is equal to negative 1/2 plus I of the integral from 0 to plus infinity of 0 by the virtue of f being even, or at least on that imaginary line. So 0 over 2 to the 2 pi t minus 1 dt. So we integrate 0, so that term will be gone. And we are left with only what is in front, like in a previous proof, negative 1/2, which is exactly what we were expecting. Proof number 7, Riemann zeta function. So the Riemann zeta function is defined as follows. Zeta of s is a sum from n equal 1 to infinity of 1 over n to the s being a complex variable. So the sum of the periodic monotonic divergent series 1, constant 1, correspond to the Riemann zeta function evaluated with s equals 0. So sigma of n equal 1, or sum from n equal 1 to infinity of 1, we can write it as a trick as sum from n equal 1 to infinity of 1 over n to the 0. And if you compare that expression with that one, you can see it's identical if we have s equals 0. Therefore, that value is zeta at 0. All right. Now, if we open the toolbox, what is the value of the Riemann zeta function at 0? It's negative 1/2. Therefore, the value of the periodic monotonic divergent series of constant 1 that we are after is equal to negative 1/2. Okay. Last proof, proof number 8, Dirichlet eta function. So the Dirichlet eta function eta of s is defined as follows. Eta of s is a sum from n equal 1 to infinity of negative 1 to the n minus 1 over n to the s. Why n minus 1? Because my naming convention has start with 1. So that's the reason. S being a complex variable. So the sum of the periodic alternate divergent series 1, also known as Grandi series, correspond to the Dirichlet eta function evaluated with s equals 0. Let's see that. We have a formula linking the eta Dirichlet eta function at 1 minus m. It's equal, for m being an integer, it's equal to 2 to the m minus 1 over m times bm, bm being the mth or m plus 1 bare unit number. And that's true for any m integers greater or equal to 1. So again, bm is a m plus 1 bare unit number in a context of b1 equal plus 1/2. Okay. Toolbox. We have, b1 is equal to plus minus 1/2. Here we are in the context of plus 1/2. For m equal 1, we have n b1 equal 1/2. Like I said, the context we are in. What do we get? The sum from n equal 1 to infinity of negative 1 to the n minus 1 equal to the sum of n equal 1 to infinity of negative 1 to the n minus 1 over n to the power 0. So again, it's a trick that we write the denominator being equal to 1, n to the 0 power. Now, if you look at this formula and compare it to the definition of the Dirichlet eta function, you realize it's the same thing for s equals 0. Therefore, that expression is nothing else than eta at 0. So we write it down. And now we use this formula. How do we get 0 for m equal 1? That's what we say here, for m equal 1. So 2 to the 1 is 2, minus 1 1 over 1 b1. 2 minus 1 over 1 b1, obviously it's b1, which we are in a context of plus 1/2, it's equal to 1/2. So now, how do we move from eta of the value at from eta at s equals 0 to the value of the zeta function at s equals 0? We use that conversion formula, of course, for s equals 0, which gives us eta at 0 equal 1 minus 2 to the power of 1, so 1 minus 2, which is negative 1 of zeta at 0. So eta at 0 is negative as zeta at 0, opposite sign. So if eta at 0 is 1/2, negative eta at 0 will be negative 1/2. And then we find again the value of the zeta Riemann function that we have seen on the previous board. So finally, the sum from n equal 1 to infinity of 1 is equal to, we write it as sum of n equal 1 to infinity of 1 over n to the 0, which is the Riemann zeta function at 0, which is, like we've seen here, negative 1/2. All right. So the bonus board, sum of the periodic monotonic divergent series of the constant c. So let's determine the sum of the periodic monotonic divergent series of the constant c, c plus c plus c plus c plus c, etc., from the periodic monotonic divergent series of the constant 1. So let's write it down, the constant 1, the sum, we have seen it now with multiple proof, 7 proof, negative 1 over 2, so negative 1/2. What do we do with that? We will do a scalar multiplication, so that little dot that's multiplied by constant c. You multiply term by term, so c plus c plus c plus c plus c, etc. So really term by term, column by column here. And then if we have multiplied by scalar c on the left, we need to do the same on the right-hand side, multiply by scalar c. So negative 1/2 multiplied by c is equal, of course, to negative c over 2. So that's it. If we write the same thing in sigma notation, it's quite simple. It's simply saying that the sum from n equal 1 to infinity of the constant c, by linearity we pass it in front, so it's c times the sum of n equal 1 to infinity of the constant 1. That we have seen through all the proofs before, that it's negative 1/2. That's what we are writing here as well. We pass that in front, and then multiply by c is equal to, of course, negative c over 2, or negative 1/2 of c. All right, so simple. And then that's the result that we need to know by heart, that the sum of a constant is equal to negative that constant over 2. And that is true not just for c being an integers or rational or real number, it can be any number. C being a complex number or even a quaternion, it will work as well. Huh? Okay. So, in summary, we have seen that the sum from n equal 1 to infinity of the constant 1, and it actually does not depend when we start the indexing. We can start from n equal 0 or n equal 10 or n equal minus 27, makes no difference because it's all the same, it will be identical. So the sum of the constant 1, doesn't matter where we index it from, 1 plus 1 plus 1 plus 1 plus 1, etc. is equal to negative 1/2. I hope you enjoyed the video. Thank you for watching.